All right, merge sort. The nice thing about merge sort, it is in log in. And I told you already that most of the time when you call a library, it uses quick sort and not something else. And merge sort is always in log in, but quick sort could become in square. So while we're doing merge sort, I'm going to ask you a question at the end. Why do you think they choose quick sort over merge sort, even though merge sort is guaranteed to be in log in? Because there's a very good reason for it, but it's a little subtle. All right. So we have those numbers. And I love this picture because it shows you exactly what's going on. It takes its numbers. First, it divides it not by a pivot, but just keeps cutting it in half. And then once you cut it down to a list of one, a very wonderful property of a list of one number is that it's already sorted, right? That's a great property. You then merge them back together. So you look at your two lists, and so that'd be 2835 and 1945, that's in order. Then how do you merge two lists? Well, you then take advantage of the property that since the two lists are already sorted, you know that the beginning value is always the lowest. So you only have to evaluate what's in the front of the list. So you evaluate the 28 and the 18, so it's 18. You evaluate 28 and 45, so 28. Then you evaluate 35 and 45, it's 45. And then you drop the 45 down. Same thing over here, you evaluate the 48 to 30, the 30 is what's smaller. Then you evaluate the 48 and 38, and then you realize there's nothing else left in that list, so you copy everything else over. And the biggest list will probably make it the most sense here. And we'll do this on the board, by the way. But I love, this picture really does help. 18 and 30, it's the 18. 28 and 30, 28. 35 and 30, it's the 30. 35 and 38, it's the 35. It's the 45 and 38, it's 38. 45 and 48, it's 45. This list is empty, copy everything else down. And now it is sorted. Let's go do our one on the board. This one is way easier to draw. Way easier. All right, so we chop it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 6, 1, 2, 3, 4, 5, 6. And I can show you how it chops up, but it's just 13, 7, 15, 2. Actually, let me draw it this way. It chops up into 2 eventually. So let's go evaluate these two. What does that become?
7 and 13.
All right. I don't know why I drew a 13 first.
2, 15. 0, 1. Same thing.
0, 9? No, I'm kidding.
Yes.
-2 and 19.
-21.
Nice, thanks. 10 and 11. Great. You evaluate. Well, we're going to do this one by memory, and then I'll show you manually how it's done next, because when it's a larger list, it's going to make way more sense. 2 and 7.
2.
7 and 15.
7.
13 and 15.
13.
That list is empty. Copy the rest of the other list.
-1.
I'm sorry. 0 and 8. Oh, no.
0. That's why I was confused.
Then I drew an 8.
8.
That list is in, so you copy the rest over.
-4. 11.
All right. Hey, look, we have an odd number of lists on that side. That's okay. We're going to merge these two, and then we'll merge that one in the big list. All right. I'm going to do this one manually just to show. We have an index pointing to the two arrays, or a pointer to whatever node, because remember this could be an array or a linked list, depending on how you want to do it. So we evaluate the 2 and the -4. The -4 is first, so in the new list we put a 4, and then we advance the pointer or the index by 1. Then we look at the next one, 0, and 2, it's a 0. So we advance the pointer or the index by 1. Then we evaluate the 2 and the 8, it's going to be the 2, so we advance this pointer by 1. We evaluate the 7 and the 8, it's the 7, so we advance this pointer by 1. Then we
Evaluate the 8 and the 13.
and it's
So,
the
goes down to 18.
goes down to
Advances
8,
the point.
and then advances this pointer. Then we,
9.
it's at the end, and that means we
Copy the
Don't-
rest.
copy the rest of this list down. Okay, it didn't perfectly match up, but that's okay. We're gonna do those two. How am I on this board? Let me make this a little higher. Great. And we'll use the pointers one more time just to drive this home. What's first?
-21. -4. 0. 2. 7. 8. 9. 10. 11. 13. 14.
Into the list, copy everything over from the other list down. Let's sort it. What's the big O? Wait, I already told you. But why is it in login?
And the login comes from the fact that it's splitting everything down per iteration.
So, in other words, well, each level, each one of these levels, how many comparisons are there? N. So there's O of N comparisons per level. How many levels are there? Do O of N, up to O of N, up to O of N. I'm saying up to O of N. But how many of these O of N comparisons are, I mean, how many levels are there here?
Right there or normally?
In big O notation. How many levels are there? So in this one you had 12 and you had 1, 2, 3, 4. But if you had 16 numbers, I'll tell you there's also 4 levels. But
Like
you have
only
17.
do it like the big picture where it splits them up that way.
Mhm.
So that's like double the amount of levels that it shows.
So this is the merge part. I'm just talking about the merge part right
Oh,
now.
okay.
So in the merge part, how many levels are there? There's basically log base 2 of n levels. Because since you're merging basically, yeah, here, it's, think of it the other way. You have this big thing down here, you're cutting in half, cutting in half, cutting in half, right? So if you look at it from the bottom up, it's the division by 2. But as you pointed out in the slides, it first divides it by 2 and then merges it back. Well, this from here to here is log base 2 of n. Actually, it's, yeah, log base 2 of n. And then from here down to here, it's the same thing, log base 2 of n. In other words, the number of levels from here up here is log of n, and same down here. So what that means is actually big O of n log n plus big O of n log n, which makes it 2 times big O of n log n, aka n log n. We don't care about coefficients. All right, so general algorithm, divide the list into 2 sublists, merge. So merge sort the first sublist, merge sort the second. You keep doing that until you have only one, and then you merge the 2 lists. Uses recursion. All right. So we'll start here. Notice that they're doing a linked list version. Here's a linked list of nodes, unsorted linked list, middle. Eventually you get to the middle and current. The way you do it with a linked list is every time you increment middle by 1, you increment current by 2. So and then when current gets to the end, middle is halfway there, right? So then you can cut off middle to point to nothing, and then the head points to the beginning, and the other head, which would be the 20, points here, and you just keep redoing that until you divided the linked list into individual pieces. And then when you merge, well, when you're coming back, if your linked list just has 2 elements, that's pretty straightforward. I mean, your linked list has, I'm sorry, let me rephrase it. You have 2 lists, each with 1 element, that's pretty straightforward. But if it's you're merging 2 linked lists that are sorted, then you just have to look at the beginning of the 2 heads. So the new head starts at 18, and then notice that it would need to make a 18, go to 20, and then, wow, it's not going to tell you. 18, then 20, 20 points to 25, 25 to 30, to 45, back to 65, then to 75, then to 85, then to 95. So you can hook this all up with a linked list as well. All right, they do the little more math that we don't get into. And it's in log n. Okay, here's the tough question. I told you that pretty much when you call sort, it's calling quick sort and not merge sort. Yet merge sort is guaranteed to be in log n. Why do they use quick sort instead? Give you a hint.
Is it memory?
It's about memory. What about memory?
You need pointers for this to like check each number.
I see what you're saying, but that's an extra pointer is not that big of a deal.
Okay.
If this is an array, on the board, great. And that's an array, and you wish to create the sorted array from those 2 arrays, what do you have to do?
Make a new array.
Make a new array. So how much memory, when you use an array, does merge sort take up?
A lot more.
Twice, because you need to have a full copy of the array in another piece of memory. How much memory does quick sort take up? How much additional memory?
0.
0. Just a couple of local variables. So quick sort is called an in-place algorithm because it sorts everything inside the data structure without having to make a full copy of it. And that is why quick sort is used, because as you'll find out in architecture, using a lot of extra memory is bad, but you'll get to that. And that is why, in general, quick sort is used, even though worst case can degrade to n squared. In general, that just does not happen. So we, 1, it does not happen, and 2, if you're smart about choosing your pivot, you can make it so the likelihood of it turning into n squared is extremely remote. So that is why quick sort is chosen most of the time. What would y'all think of merge sort, by the way?
It's easier to understand, I think.
Way easier to understand. The quick sort works because of how a computer works. Merge sort, it's a little easier to, yeah, it's just easier to follow. You're like, oh, we're just merging things. Oh, okay. Quick sort's like, we're putting this right here. Okay, sounds great. Why are we doing that?
So this would be better for a linked list then, because there's no extra memory. It's just moving pointers.
Yep, you nailed it. If you're sorting a linked list, you want to use this algorithm. If you're sorting an array, use quick sort. If you have additional information about your data structure, go research the hundreds of sorting algorithms there are and pick one. Because there are, depending on your data structure, there are O of n sorting algorithms, but there's no general purpose, we call it comparison-based algorithm that's better than n log n. So far I'm just assuming that all you know is if you can tell if one number is less than another. And so based on that you have, what is it, quick sort and merge sort. By the way, we are going to go through one more sorting algorithm that is also in log n. and it can be used, but in general, people just stick with quicksort. All right. Let's see, summary. Sequential search is terrible, but if we sort everything, then we can do a binary search, which is log n, but that requires us to sort it. Well, sorting is n squared, which is not great, except for quick and merge are both n log n, and we've talked about the differences between the two, and I think you've mentioned quick sort is good for, well, which one's quick sort good for? Arrays. And which one's merge sort good for? Linked list. So,
I'll show you.
good job. And that's great you already chose that, because that's part of your lab, and you pointed that out. Great.
You can still do select sort for linked list though, right?
Oh yeah, you can use all the sorting algorithms. It's just which one's actually going to be more efficient based on how things are laid out. Yes.
So which would be quicker, just searching the whole list for whatever you're looking for, or manually sorting it and then doing a viral? Well,
If you're
not
doing
manually, but-
one search, obviously the sequential search is faster. But if you're going to load in a bunch of data like in a database, and then once it's loaded, you're not going to change it very often, but you're going to ask, like, do we have this value? What about this value? What about that value? How many numbers are between these two values? You're going to want to sort it first, because log base 2 of n is way, way faster. So, in other words, it depends.
It's always the answer.
Pretty much. That's always the answer. Great question. Any other questions? All right.